Welcome to Module 2.4, where we'll dive deep into the intricacies of smart contract composability and its pivotal role in DApps, DeFi, and the broader cryptocurrency landscape. Composability sounds complicated, but the concept is actually quite simple. Think of it as using existing software pieces, much like Lego blocks, to craft new applications. Just as you'd assemble various Lego pieces to create diverse structures, developers leverage these software components to build novel applications. In Ethereum, each smart contract functions like a Lego block. You can employ these existing contracts as foundational elements for your projects. For instance, take the decentralized exchange Uniswap. You can integrate its smart contract to provide token swaps in your own DApp. This not only saves you from creating a smart contract from the ground up, but also dramatically streamlines application development. That's why composability in software is often compared to compounding interest in finance, a principle of exponential growth and efficiency. So how does composability function? The principle of smart contract composability stands on three pillars: modularity, autonomy, and discoverability. Modularity implies that every component, akin to individual Lego pieces, serves a distinct purpose. In Ethereum's context, each smart contract addresses a particular use case. Autonomy refers to the capability of components to operate without external dependencies. This holds true for smart contracts as they are self-executing, operating without the need for other system parts. Lastly, discoverability emphasizes the open-source nature of smart contracts. They are accessible for everyone to view and invoke. Without this public visibility, developers would be hindered from detecting and interacting with other contracts. Another critical infrastructure element that enables composability is standardization. Although Ethereum's architecture was designed to facilitate composability, it doesn't automatically guarantee the compatibility of functions and interfaces across different DApps. This is why application-level standards have been established through a protocol called Ethereum Request for Comments, commonly known as ERC. These are documents that describe rules for Ethereum-based tokens, which programmers use to write smart contracts. Some of the most popular include ERC20, ERC721, and ERC1155, each for issuing different types of Ethereum tokens. Let's explore real-world examples to understand Ethereum's composability. Suppose you're crafting a DApp where transactions are typically in Ether. By weaving in the token swap functionality from an established smart contract like Uniswap, you can allow payments in other ERC20 tokens within your DApp. Similarly, if your aim is to set up a governance structure for a DAO, rather than investing resources to originate one, you can swiftly leverage open-source platforms like the Aragon client. In the domain of identity management, open-source solutions offer sign-in with Ethereum features, empowering users to verify their identities using their Ethereum wallets. There are different kinds of composability. What we have discussed so far can be categorized as syntactic composability. Another type of composability is atomic composability, which refers to the situation when several operations across multiple DApps can be bundled into and executed in a single transaction. If one operation fails, then the entire transaction won't be executed. This makes it possible to create innovative DeFi services such as flash loans or split a transaction across multiple exchanges. Composability isn't limited to just smart contracts. It extends to DApps, DeFi, and DAOs. The underlying concept aligns with our discussion on smart contract composability, but finds broader applications. In DeFi, for instance, composability denotes the capacity to combine, structure, and stack various financial services together. What's the benefit of composability? As we've seen, it reduces the work that developers have to do when creating DApps, and therefore saves time. This also means developers can spend more time experimenting with new features, leading to greater innovation. In the end, users can enjoy different functionality across different networks. Of course, composability faces a number of challenges. Security issues are a top concern. Composability derives from the ability of smart contracts to call other contracts. But as we've learned in the last module, calling external contracts could lead to exploits if the external contracts are malicious or have security flaws. Another potential challenge is related to intellectual property protection. Smart contracts are open source and discoverable, which makes composability possible. But there are signs that this might change. Some smart contracts have added clauses into their code to prevent unauthorized usage or forking. If more smart contracts add such a clause, it could compromise the discoverability of smart contracts. Adequate standardization is another core requirement for composability to thrive. The Ethereum ecosystem has robust standardization to ensure interoperability and composability. However, with the expansion of blockchain networks supporting smart contracts, it could be a challenge to establish cross-chain standards to achieve composability. In the next section, we'll move on to explore decentralized autonomous organizations, an innovation that is making decentralized governance easier for greater adoption.